All right, so let's talk about kinetic energy again. Spoiler. Sorry, did not ask you. All right, so we dealt with this in the previous, in 2 chapters ago, chapter 7, I guess. And that's all well and good if an object's traveling in a linear fashion. However, if I've got a bar here rotating about a top point, so this thing is swinging, what's the kinetic energy?
Would the equation be 1/2 moment of inertia omega squared?
It would be. However, what does that mean? Besides 1/2 times the moment of inertia times the angular speed squared.
So
Every moment, like if you met the average, or like when you have anywhere around the circle, if it's perfect circle, it would be the same amount of angular speed. It would just stay constant, so it's a full circle. Kind of what we did with when we swung the things.
Okay. Yeah, all right, so the angular speed would be constant, but we need to somehow use this to figure this out. We're basically going to derive the equation that Ibrahim just mentioned, using this idea that the angular speed is constant. All right, so if I want to plug this into that equation right there, recognize that the speed varies depending upon where I am. This point right here, if it goes around an entire circle, has a very far distance to travel, whereas this point right here doesn't travel very far at all.
So what is moving?
What is what?
What is moving in this situation? Do we know? The whole is
The
it
whole-
like the whole stick?
Yeah, except for that one point at the top.
Okay.
So basically this.
Okay.
So what would you use for speed? I mean, the mass of the object, and you stick it on a triple beam balance, but, and this is supposed to be uniform, it's not supposed to look like a baseball bat. Closer. What would you use for speed for an object, since the whole thing is traveling at different speeds?
angular speed.
I can't just stick an omega in there and be done.
Oh wait.
Well, not legitimately.
Can you use pi?
All right, let's dial back for just a second. If I had to choose an average speed, where would you pick? Okay. So I could take the middle. So I could come up with a crude estimate here of that the kinetic energy of this object is 1/2 times the mass times the speed of the center squared. It's a crude estimate. I could get a little bit more accurate if I treat this as 2 different objects, and I pick the center of each of those objects, and so my kinetic energy now, it's a better approximation. 1/2 times, I'm gonna call it mass 1, call that mass 1 and mass 2. Mass 1 times the speed of the center of 1 squared plus 1/2 mass 2 times the speed of the center of 2 squared. So this has its own speed, and that has its own speed.
What if you like infinitely cut it up?
And that's where we're headed. We can get into more accuracy if we keep breaking it up into more and more parts. So I'm gonna write it out in longer notation, then I'll shorten it. So M1 V1C squared plus 1/2 M2 V2C squared plus 1/2 M3 V2 V2C V3C squared plus however far I want to take it. The shorthand notation is I'm doing a repetition of the same thing over and over again. I'm adding a repetition. So I'm going to use the capital sigma here to represent sum. And I equals 1 to however many parts I break it up into. If Ibrahim's doing it, infinite number of parts. 1/2 mass sub I, V sub I. I'm just gonna drop the C. At some point, the masses are so small that the center of mass is the mass squared.
When we use that symbol, the sum symbol, whatever you call that,
Sigma.
sigma.
It's capital sigma.
Okay. Do we need to write the n in the 1 = 1 thing?
You need to somehow give, officially you need to give limits. If you don't write it, it's assumed this is 1 and that is infinite. Or if you, it depends on how you want to interpret your own handwriting.
Okay.
Officially, yes. From a practical point of view, oftentimes physicists will just drop that stuff because you're just supposed to know.
Okay. So it's, the n basically stands for infinity, and it's supposed to be.
N is whatever the upper limit is, and it is infinite.
Okay.
And what does the I equals 1 mean?
That's the starting point.
Am I starting?
We start with, we stick 1 in here for I, plus, then we go to the next number, 2,
Oh, I see.
next number 3, and so forth. And we keep going until we get up to N.
Okay.
In computer languages, for I equals 1 to N. Something, 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 and if. Other questions right now?
I never thought I'd see that simple until I get to calculus.
All right, at this point, it becomes obvious. You take any object, break it up into an infinite number of pieces, find the speed of each of those pieces, add them all together, the kinetic energy of each of those pieces, and done. However, that might seem difficult of adding up an infinite number of things. Now recognize you're adding up an infinite number of infinitesimally small things because the more parts you break it up into, the smaller the mass of each part is.
Will it eventually get to 0? Or like,
No, it approaches 0 but does not equal 0. There's a huge distinction between infinitesimally small and 0. All right, next step. Let's work on the idea that the angular speed is the same for all the objects. So right now we are dealing with what's known as a rigid body. We are keeping, at least that assumption is that everything in there has the same angular speed, that it's not rubbery and part of it's traveling fast, you know, and it works. What is the relationship between the linear speed of any part on here, let's just say this point right here, the linear speed of that point and the angular speed? What is the relationship?
Of the same spot.
Of anything that's rotating, what's the relationship between angular speed and linear speed?
it's gonna be, oh, what it was the thing? Oh, angular speed equals velocity over R.
Speed.
Speed.
Over R. All right, so we have this relationship right here. You remembered it from the centripetal motion?
Yes.
Or V equals omega R. So whatever the angular speed is, you multiply times the distance from the pivot point, and you get the linear speed. If you wanted something more formal than that, as some of you might, if I have an object that is rotating around, the speed is the distance over time. The distance it travels going around once is 2 pi r, where this distance here is r, divided by, I'm going to use a capital T for period. The angular speed is equal to the change in the angle over time. And what angle does it go through as it goes around once?
360 degrees, or 2 pi radians.
So 2 pi over t. Well, the difference between them, if I multiplied omega times r, I would get this. So omega r is equal to 2 pi over big T r, which is just t.
So, what does big T stand for again?
Period.
Period.
For repetitive motion, it's the time it takes for one cycle of the repetitive motion to happen. And therefore,
big T is how long it takes for one cycle of motion?
Yes. So that becomes the sum of 1/2 m sub I times, omega r sub I squared. Now notice that I don't have a subscript next to omega because omega is the same for everything.
Is that omega over there, is that omega r
Yes.
equals 2 pi over big T r equals
Z. Now remember that this is a sum. It's a sum of n, capital N different things. And if I have any common factor, I can just factor it out. So I know that all of them have a half in it, all of them will have this omega in it. I can't factor out m because one will have m1, another will have m2, another will have m3. They're sort of all not necessarily the same mass. So I'm going to factor the 1/2 omega squared out. That's the omega squared. And what I'm left with is 1/2 m sub I, not the 1/2, the sum m sub I r sub I squared.
So the big sum symbol can be in the middle of an equation?
Yeah,
And so it's a function? Kind of? Because you have the 1/2 thing, or omega squared before it. So you can, like whenever you put it, it excludes what's before or after. No.
Let me just take this example right here.
Okay.
I got a 1/2 common to two of them. So I can write this as 1/2 times m1 v1c squared, v1 squared plus m2 v2 squared. So I just factor the 1/2 out. Now my infinite sum doesn't include the 1/2.
Yeah.
So in essence, I did the same thing. The 1/2 and omega squared is going to be common for every factor. I can bring it out. And so this sigma, so
Okay.
I'm adding up that sum of just that part.
So I can kind of think of it as a function.
Yeah, I'm trying to think of whether it officially categorizes as a function, but yeah, you could. On many levels you can, and I don't know for sure whether you can on everything. So we just have the sum of mr squareds. That makes this a whole lot easier. Now you might be looking at that, so I'm still breaking it up into an infinite number of pieces. How does that help? Well, this right here is the moment of inertia. Okay, great, we have a name for it. How does that help? Every textbook, beginning textbook, is going to have a chart, and I don't know what page it is on New Earth at the moment, but they'll all have a chart where they have already done this. They've already done this calculation for certain objects. So if I have a disk or a cylinder, doesn't matter what the thickness is, rotating about some central axis right here, or I guess from a side view, rotating about an axis there where it has some mass m and a radius r. The thickness does not matter in this situation. The moment of inertia is 1/2 times big M R squared.
So
Okay.
each shape has its own thing.
Yes,
So it's kind of like
each shape and axis of rotation.
so it's kind of like I guess area.
Like what?
Like area, they all have their own equations.
Yeah, except it makes it more complicated because that rotating about that central axis has its own moment of inertia. If I take that same disk and rotate it about an axis here, I'm gonna have a different one.
Okay.
This will be 3/2 mr squared. Now, how I got this, we'll have to wait till Thursday. Sphere. Solid sphere. I is equal to 2/5 mr squared. Hollow sphere, 2/3 mr squared,
So,
and so on.
for the solid sphere and the hollow sphere, how does it change even though if the points are the same?
How does it change?
Yeah. The mass changes, I guess?
The mass distribution changes. In the solid sphere, I have more mass close to the axis, and remember that this r squared, this r has a much greater impact.
Mhm.
So the closer mass is to the axis, the lower the moment of inertia.
Okay.
So for example, I have these two right here, they weigh the exact same amount, but the mass distribution is different. This one you should see sort of empty right there,
Mhm.
and down there, and it's blackened here. That's where the mass mostly is.
Mhm.
This one is blackened on top, and it's empty in the middle. So this mass is distributed here, this mass is distributed here.
Mhm.
I take the two objects, and I can just swing them back and forth. That hurts. A little bit better. I hurt my elbow years ago. So this one's a lot harder to get moving and a lot
Yeah.
harder to stop. This one's a lot easier to do.
Okay.
Lightsabers.
Pardon?
Lightsabers.
Yes. Sorry. I was thinking, who was a really cruddy actor in episode 2? Christian Haydenson?
You don't like Anakin?
I like Anakin. I think the actor did horribly.
Okay.
Part of George Lucas is to blame for some of it. But he talked about the first time they brought out the lightsaber, and that when he started to act with it, he was making the noise. And they said, no, we'll do that post-production.
Leave that to production.
Anyway. On Thursday, we will get into the parallel axis theorem, which would show how we got this, and we will go to the races. We will do some non-monetary gambling.
Indeed, so. The next test is going to be on what chapters?
Everything. Officially, we started with energy after the last test, so energy, momentum,
6, 7, 8.
energy, momentum, rotation, harmonic motion, and possibly some thermal, maybe some fluids.
So literally everything else.
Yep, I think that's something. As we get closer, we'll know better. We just went through, I mean, the last couple of times I've done 151,